Good afternoon. First of all, I would like to thank the organizing committee for the opportunity. This is a joint work with Vitor Fossalusa and Igor Amario from IMUSP and a colleague of mine, Marco Chain, at EASH USP. Intentional or purposive sampling methods are non-randomized methods that select or allocate groups of individuals with the purpose of meeting specific prescribed criteria. In our case, it could be the representativeness of the sample or balance between groups. Such approach is intended for exploratory research in cases where tight budget constraints or low availability of individuals preclude the use of traditional randomized representative sampling. However, intentional sampling poses several questions concerning statistical inference. The first of all is the validity of the assumed models in the absence of the randomization. The second one regards to possibility to human interferences, conscious or unconscious interferences in the process. Bazou states that a way to deal with this dilemma is to make the plan very purposive, but to leave a tiny bit of randomization in the plan. The expression haphazard sampling or design is known by, was coined by Lindley. In this presentation, we introduce a mixed intentional randomizing framework for sequential allocation for multiple groups and show some empirical results in a case study of software evaluation. This is an extension of sequential allocation methods for clinical trials already present in previous works. The objective of fault localization is to help developers in their debugging activities. Igor de Souza proposed a new tool for fault localization for Java programs. The name of this new tool is Jaguar. The evaluation consisted in comparing this new approach to the standard debugging technique for Java called JUnit. Each invited participant had to use Jaguar and JUnit, each one with different faults. The group we had 4 experimental groups, each one corresponding to a different order between debuggers and between faults. For example, group 1 started with Jaguar on fault 1 and finishing with JUnit on fault 2. And so on. The endpoints of interest was success or failure in finding the fault with each debugger, and they spent time with each debugger. One important aspect here is that the success or failure in finding the error is strongly dependent on the experience of the developer in Java, in IDE, the integrated developed environment tools, and testing. So we had to balance these prognostic factors between groups. This is a scheme for the experimental workflow. After answering the questionnaire where the volunteer answered about his Java experience, IDE, and testing, we had to quickly allocate this person to one of the 4 experimental groups. We have here some notation, but in essence, the main information we deal here are the frequency table of volunteers according to group allocation and according to experience level on Java, on, you see a typo here, here, in IDE and testing. So, for example, here we have the absolute frequencies of individuals already in the study that has, for example, basic level, experience level on Java, and is allocated to group 1, and so on. This is essentially a frequency table for each variable. We have already, we also introduced an artificial variable for trying to yield similar group sizes, because the distance measure we use in this study is independent or invariant with respect to scale. So we have to introduce here tricky for deal with this problem. I have no time to explain details, but this essence is to for artificial vectors in such a way that the frequencies or the proportions of individuals in each group would be the same. Each individual participant is represented by a characteristic binary vector representing its corresponding category on each variable, and adding a participant into a group I is simply the same to add that vector to the corresponding rows in the matrix frequencies, in the contingency tables. PJ, PI, and so on correspond to proportions, to transformations of absolute frequencies on relative frequencies of individuals according to each group allocation. This is a normalization in each row of the matrix frequencies. Our measure of global dispersion for each matrix proportion is an extension of allocation distance, in this case the sum of variances between the log ratios between proportions in each group. The final heterogeneity measure between groups is essentially a weighted mean between the distance in each variable. The procedure consists essentially in, we have a characteristic vector of the new participant. We have a perturbation parameter, which I will explain in a bit, in a few minutes. Essentially, for each of the 4 groups, we add the participant X into that corresponding group. We create here an artificial or a random matrix in such a way that it's easier to show graphically. This is an artificial matrix where for each group we generate a uniform variant here, and it's complemented in such a way that we have the proportions in the simplex. And this serves like a coin, actually. And what we do essentially is to combine compute a convex combination between the deterministic distance among the 4 groups, among the proportions in groups, and the distance computed over this random matrix in such a way that the perturbation parameter acts like a balance between the randomized allocation and the purposive allocation. Epsilon equals 0 means that we are on the purposive sampling or allocation. Epsilon equals 1 means that you have pure random allocation. The final allocations correspond to the group that minimizes this distance. Well, the problem here is to choose the value of epsilon. We have two optimality criteria or two performance criteria for doing that. The first one, which is obvious, is the optimality criterion, which is based on the distance between groups and concerns the participants' heterogeneity between groups. So in other words, we want that this distance is as low as possible. Our benchmark is the deterministic intentional allocation scheme. It's almost impossible to give a better solution than that. On the other hand, we cannot expect that, or another objective is that each possible each possible set of allocations for the same permutation of individuals, ideally they should result in different allocation groups. So we don't expect a high concordance between different allocations for the same sequences. This is measured in our work by the Fleece kappa, which is a measure between minus 1 and 1. Kappa equals 1 corresponds to the full agreement between different allocations, what for sure is the case when you perform the purposive sampling, the pure purposive sampling. And kappa equals minus 1 means the full disagreement. Of course, we don't have none of them. You have the ideal point here is about kappa equals 0, which means random or no association at all between different allocations. Our benchmark is pure random allocation method, which you cannot do better than flipping the coin for giving non-associated or non-correlated different allocations. Well, so the approach for choosing epsilon essentially is to try different values of epsilon and try to measure the distance between groups and the kappa, Fleece kappa, for measuring the decoupling. This is a graph representing the final distance between groups, or distance yielded by the allocation with different values of kappa. Pure random corresponds to epsilon equals 1. Epsilon equals half, 0.2, 0.1, and so on. The intentional allocation means epsilon equals 0. Here, for that, as we don't have a priori knowledge of real data, we had to simulate the artificial data for calibrating this curve. In this case, we simulated data with 50 volunteers, with 300 samples and 300 allocations per sample. Here we have the percentiles of distance curves according to the values of kappa. Our main the main interest may be on the median of the distance and the 95 percentile of distance. Here, we have the distance for pure random allocation, which means the highest distances. With haphazard, epsilon equals half, 0.2, 0.1, and etc. Obviously, we would like to have, for example, the smallest distance possible. In this sense, for example, the value is 0.02 achieves distance as good as the pure, the intentional allocation. But on the other hand, in this case, we have now looking for kappa, for the association between between different allocations. We have here high values of kappa, which means high association or high predictability of allocation. What's bad characteristics? Here we have, as you see, the lowest possible values of kappa, which correspond to pure random allocations. For high values of epsilon, we have almost the same association found in kappa, but if you accept a bit of correlation with anyway is very low, below 0.1, in this case, for example, epsilon equals 0.1. In this case, you have a small penalty in kappa in association, but on the other hand, you have a very good approximation of distance with the optimal solution. So, in this case, we elected kappa equals 0.1. Well, after we had find the best value of kappa, offshore, you have to see how is the performance on real data. This experiment, unfortunately, didn't achieve too many volunteers. Only 48 have participated on this study. We have simulated 300 permutation from the original sequence in order to evaluate the variability or the uncertainty related to different sequence of entrance of new participants. What you see here is specifically for Java experience frequencies. This corresponds to the average frequency of individuals allocated, of individuals of basic experience allocated to group 1, 2, 3, and 4. Individuals of intermediate experience and the individuals with advanced experience. So, on average, what we see is that on the average, all these methods tends to provide very equally balanced groups. Of course, our objective is to make that the obtained groups are the most homogeneous, or what means the same frequencies in the four groups for each level. Well, what happens is that the concern here is regarding to the variability. In red, you have the variability, or here is expressed in terms of 1 plus minus 1 standard deviation for pure random, which means a high variability. Here, for haphazard, with epsilon 0.1, which is much smaller, and the pure intentional allocation. What we see is that in several cases, the epsilon equals 0.1 achieves almost the same variability that would be possible with the intentional allocation. Here we have on Java, on IDE, for example, in this case, there are no participant with no knowledge of IDE. the same characteristic, and the same here on testing experience. So these results show, indicate that under an appropriate calibration of the perturbation parameter, you can actually conciliate the performance of optimality achieved by the deterministic intentional sampling and the decoupling or absence of interference that is provided by pure random allocation. Next steps are establishing or finding ways for calibrating epsilon, and we are already working on the next steps that regards on inference methods. Thank you.